This video is perfect for beginners who are interested in learning more about quantum computing and how to use Python to develop quantum applications. In this video, you will learn how to develop your first quantum computing application using Python. You will also learn the basics of quantum computing, how to use a quantum computing framework, and how to test your code on a quantum simulator. By the end of this video, you will be able to understand the basics of quantum computing, use a quantum computing framework to design and build quantum circuits, and test your quantum computing code on a quantum simulator. Quantum computing is a rapidly developing field with the potential to revolutionize many industries, and there are many opportunities for innovation. If you are interested in developing quantum computing applications in Python, I encourage you to get started today. Can I test a quantum computing application on my laptop? Yes, of course, you can test quantum computing applications on your laptop using a quantum simulator. A quantum simulator is a software program that simulates a behavior of a real quantum computer. There are several different quantum simulators available, including Qiskit Air, Cirq Simulator, PyQL Simulator. To test a quantum computing application on your laptop, you will need to install a quantum simulator and a quantum computing framework such as Qiskit or Cirq. To install Qiskit Air Simulator, you can use pip install Qiskit Air on your terminal. Once you install the quantum computing simulator on your computer, you can start simulating your first application. Here are some additional tips for developing quantum computing applications in Python. First, you get started with simple examples. Before you start working on a complex computing or quantum computing application, it is very important to start with simple examples to get a good understanding of the basics and use a quantum computing framework. A quantum computing framework will provide you with the tools you need to design, build, and run quantum circuits. Test your code. It is important to test your quantum computing code thoroughly to make sure that it is working correctly. Use a simulator before you run your code on a real quantum computer. You can use a simulator to test it and make sure that it is working as expected. To test the first quantum computing application on your laptop, watch the next video. Here you will learn the basics of quantum computing, how to use a quantum computing framework, and how to test your code on a quantum simulator. By the end of this tutorial, you will be able to understand the basics of quantum computing, use a quantum computing framework to design and build quantum circuits, and also test your quantum computing code on a quantum simulator. This video is perfect for beginners who are interested in learning more about quantum computing and how to use Python to develop quantum applications. To start and test your quantum computing applications on a simulator, first install Qiskit's Air library, Python library. To install this, you can use pip install Qiskit's Python AR. Here is Qiskit. There, and it's going to install this library on your laptop. Then once you install that library, then you can start importing the module or library or the framework in your Python script using import Qiskit's library. Okay, next is create a quantum circuit with 2 qubits. You can define a circuit by creating 2 qubits using Qiskit dot quantum circuits and pass to this is a 2 qubits quantum circuit. Okay, then the next is apply a Hadamard guard to the first qubit. that is the first qubit is at index 0, that just use circuit.h and pass 0 to that to apply a Hadamard gap to the first qubit. And the next is create a classical registers and allocate classical bits. In this case, you can create a classical registers, allocate the classical bits. It is 2-bit and name it C, that is a classical qubit. And once you register classical register by allocating the classical bits, you can add register to the circuit. Okay. So the next is measure the qubits and store the measurement results in the classical bits. So circuit.measure, you always the states are zeros and ones in this case. So zeros and ones, and the classical registers here, classical register at index 0 and at index 1. At index 0 is 0, at index 1 is 1. So now it's going to measure the circuits at classical bits, and the next is simulate the circuit. Simulator, that's Qiskit dot air dot get backing. You can use Qasem simulator in the backing, and it's going to just execute the circuit function here defined, and the simulator here that's going to simulate the circuit, and it's going to just return the result as a result method. And you can obtain the number of counters, how many number of circuits that measures in the zeros and ones states, and it gets the measurement results by calling result.getCounts. Finally, you can print out the counts to see the output. So in this case, if you are using different computing framework, you should consult the documentation for that framework to learn how to install and how to define your first circuits or quantum application with Python. So this is your first quantum application or script to simulate a quantum computing on your laptop using Python. And once you have installed your simulator, and you can test it by running this code, by writing any text editors or script writing editors, especially you can use Visual Code Editor to edit it. It is normal Python script. If you know Python, it is easy for you, and you can define the functions and the circuits and qubits, and it's going to measure the states. So this code will simulate the quantum circuit and print the probabilities of measuring the first qubit in the state of 0 and 1. Then if you are able to run this code without any errors, the simulator has been successfully installed. And let me show you by running this code. You can use this to run. So it's just printed out the result as a dictionary, and it's important to note that simulators are not as powerful as real quantum computers, but quantum simulators cannot simulate large quantum circuits, and they may not accurately simulate the behavior of real quantum computers. However, quantum simulators can be useful for testing and debugging quantum computing applications. So this is very useful to test your first quantum computing, and also you can debug any errors in quantum computing applications before running in a real quantum computer. If you are interested in developing quantum computing applications, I encourage you to start by testing your application in a quantum simulators like Qiskit Air simulator or any SARC simulator. And once you have tested your applications and you are confident that they are working correctly, you can then consider running them on a real quantum computer. Okay, as you can see here, this is the outputs that represented the measurement result of a quantum circuit. So each key in the dictionary represents possible outcomes, that is a bit string, and the corresponding value represents the number of times that outcome was measured in a quantum circuit. For example, in your case, 00 measures 505 times, and 01 measures 519 times. So this results indicate that when you run your quantum circuit with the given code, it produces a superposition of states, and when measured, it results in approximately equal occurrences of both 00 and 01 states due to the Hadamard guards applied to the first qubit. The actual counts may vary slightly due to the probabilistic nature of quantum measurements in a simulator or real quantum hardware. So this is your first quantum computing applications that measures the circuits by running your first application or your laptop using quantum computing simulators in Python. So I hope you enjoyed in this video. Don't forget to like and share. Thanks for watching. Hey everyone, and welcome to this tutorial on quantum circuits with Qiskit. My name is Asaba. I am a Python developer focusing on machine learning and quantum computing. In this tutorial, I will walk you through step-by-step guide how to construct and run quantum circuits with Qiskit in Python. Qiskit is an open source software development kit for quantum computing. Initially was developed by IBM. It provides a high-level Python interface for constructing and running quantum circuits on a variety of backends, including quantum computing devices. Quantum circuits are a way of representing quantum programs. They are made up of a series of gates that separate on quantum registers. Quantum registers are also a collection of qubits, which are the basic units of information in quantum computing. In this tutorial, you will learn how to use Qiskit to construct and run simple quantum circuits. Don't forget to like, share, and subscribe, and also write comments in the comment section of this video. You'll also learn about some of the key concepts in quantum computing, such as superposition, entanglement, and measurement. If you are interested in learning more about quantum computing, I encourage you to watch this video. The topics that will be covered in this tutorial are construct multi-qubit quantum circuits, register with Qiskit, measure quantum circuits in classical register, use single and multi-qubit gates, use barrier operations, return the circuit depths, extend quantum circuits, and finally, I will show you how you can print the constructed quantum circuits in human-readable format using OpenQSM string. Before we get started, you need to install Qiskit on your Jupyter notebook. If you are not installed yet, you can use pip install Qiskit. Then you can import the necessary classes from Qiskit module. Here, we are going to use quantum circuit class, quantum register class, and classical register class. So you need to import those classes from Qiskit module. Then the first step is construct a multi-qubit quantum register. You can use a quantum register class from Qiskit to construct a multi-qubit quantum register. To do this, you can use the quantum register class. Then you can pass two parameters into this class. The first one is the number of qubits, and then the name of the register, QR. These parameters are very important. Once you run this line of code, the quantum register named as QR with 2 qubits can be created. This register serves as a container for qubits in a quantum circuit and enabling the implementation of quantum operations and computations on the qubits within the circuit. So first of all, you need to create a quantum register with multiple qubits and the quantum registry name. The next step is measure quantum circuits in classical register. This can be done using the register class, classical register from Qiskit. This also can pass two parameters: the qubits that can be stored or measured as a result, and the name of the classical register, which is C. So a classical register with 2 qubits is created. This classical register is used to store and hold the measurement results obtained from the quantum circuit qubits. In this case, the classical register has 2 qubits, which means it can be stored the measurement results of 2 qubits. And C represents the name of the classical register, which can be used to identify the register within the context of quantum circuit. Once the classical register is created, it can be associated with the quantum circuit for measuring the qubits. Then finally, we can use the measure method that used to associate specific qubits with specific bits in the classical register, which allowing the measurement results of the qubits that to be stored in the classical bits for further analysis and processing. Now we go to the third step. Once we construct the multi-qubit registry and measure the quantum circuits in the classical register, we can create a quantum circuit. To create a circuit, you can call the quantum circuit class from Qiskit and pass 2 parameters to this function. The parameters are the quantum registry and classical registry. Now we are constructing the quantum circuit and the 2 qubits quantum registry and 2 qubits classical registry. In this case, the quantum circuit is being created. The quantum circuit function is used to create a new quantum circuit and provided with a quantum registry and classical registry as arguments. This quantum circuit will operate on the qubits from the quantum registry and store the measurement results in the classical registry. It serves as the canvas for applying quantum gates and executing quantum algorithms. Now we can use single qubits and multi-qubit gates. To use a single qubits, we can use circuit.h and QR at index 0, which is H gate, and the other is the second qubit is at position, or the second position, which is QR at index 1. This is also called Pauli's X gate. So the first one, circuit.h function, applies Hadamard gates to the qubits stored in the first index of quantum registry, QR. So the Hadamard gate is commonly used in quantum computing to create superposition, an essential concept in quantum algorithms. And the second one is, sorry, this is not X, Pauli X gate. This applies a Pauli X gate to the qubit stored in the second index of quantum registry, because we have stored two qubits in the quantum registry, which is the first index in the quantum registry, that is Hamadar gate, and the second one is the Pauli X gate, which is stored in the second index of quantum registry. So this X gate, the X gate to the qubit stored in the second index of the quantum register, the Pauli X gate is a fundamental single qubit gate that corresponding to essential bit flip, and is often used for simple quantum manipulation and demonstration. So this is so-called single qubits, that is applies the superposition, which is an essential concept in quantum algorithm. Okay, now the next is use multi-qubit gates. This is a little bit different from the single qubit gates. In this case, we are going to use circuit.cx function, and we pass the qubit stored in the first index of quantum registry 0, and the qubit stored in the second index of quantum registry. So this is called C naught, controlled knot, C naught gate. So this applies a controlled NOT gate to the qubits stored in the quantum registry at position 0 and position 1. The CNOT gate is a fundamental 2-qubit gate in quantum computing that can perform an operation on a target qubit on the state of control qubit. So in this case, the qubit at index 0 is used as the control qubit, and the qubit at index 1 is called the target qubit, because it is multi-qubit gates. So that is called controlled NOT gate. So the application of the CNOT gate can create entanglement. So this can create entanglement. But the first one was created superposition. The two concepts are very, very straight and essential in quantum computing algorithm. Okay, then we can use barrier operations in quantum circuit. So to use a barrier operation, we can code circuit.barrier function. This method that inserts a barrier in the quantum circuit, it is a visual aid and does not affect the quantum computation itself, and also the barrier separates the operation before and after it, which helping to organize and visualize different stages of the quantum algorithm or circuit. Now we can call the method measure circuit dots measures that measures the quantum circuits, which holds the quantum registry in the classical registry we have defined earlier. So we call quantum registry and the classical registry here. So this method in Qiskit actually the qubits in the quantum registry QR with the classical bits in the classical registry CR for measurements. Because the classical registry holds the measurement results of quantum qubits in the quantum circuit. So this operation measures the qubits and stores the measurement results in the classical bits. So the measurement results represent the state of the qubits after the quantum computation. And they are crucial for retrieving classical information from the quantum computation. Now we can return the circuit's depth, the path of the circuit. So we can print circuit's depth, circuit dot depth function from Qiskit. So this returns integer representation that representing the depth of the quantum circuit, indicating the length of the critical path or the longest sequence of quantum operations in the circuit. So this is very essential. So this is the depth of the quantum circuit, which is 4 in this case. It may be 3, it may be 5. So it is not always constant. Okay. So which means this is the longest sequence of quantum operations in the circuit. That's very important. You can print out the circuit depth, look like this. Now we can also extend quantum circuit. Now we have constructed the quantum circuit, but we were used 2 qubits, and we can extend that quantum circuits using this method. Okay, let's apply this extension of quantum circuits. We can use quantum register method, and we pass the qubits that we want to extend. For example, in this case, I want to extend 1 qubit in the existing circuits. So the previous was QR. Now I can use different name. Okay, Q2. Let's say Q2, and this quantum registry is QR2. Previously was QR. Now I can add the registry into the circuit using add register method, and I can pass QR to that request circuit. Okay, now is added, and I can also use the single qubit gate, Hadamard gate or H gate. So I can use, I have only 1 registry, 1 qubit, so which is stored in the first position only. So I can use QR2 at index 0. All right, now I have constructed my own quantum computing circuit. I can now print out the circuits in human readable format using open QSM circuits dot QSM. As you can see, this is the circuit I have constructed in this tutorial. So everything is readable. In the initial, I have constructed quantum registry with 2 qubits. Then this is quantum registry, the second extended quantum registry here, which has 1 qubit. I have also created a classical registry with 2 qubits. Then I used a single qubit gates. I also used multi-qubit gates, which is T-naught gate. T-naught gate. And I also used barrier measurement that measures the circuit result. And finally, this is a single qubit, which is extended in the existing circuit. So this is the circuits I have built in this tutorial. So you can practice using different qubits. You can use 3 qubits or 1 qubit or 4 qubits. So I hope you enjoyed in this tutorial and learned something new. If you have any questions, you can ask in the comment sections of this tutorial. Don't forget to subscribe to my channel for more tutorials on quantum computing and other artificial intelligence topics. Thanks again. Hey everyone, and welcome to this tutorial on fundamentals of quantum computing with Qiskit. Day 2 is about executing quantum circuits with Qiskit in Python. In this tutorial, you will learn how to execute quantum circuits with Qiskit in Python. Your feedback is matters. If you found this tutorial helpful, please like, share, and subscribe for more quantum computing and AI topics. Leave your questions in the comments below. Quantum computing represents a revolutionary paradigm with the potential to solve complex problems that are intricate to classical computers. One of the primary platforms for quantum computing development and simulation is Qiskit, which is an open source quantum computing software development framework from IBM. With its powerful features, Qiskit enables us to create, manipulate, and execute quantum circuits on simulators or real-world quantum devices. By the end of this tutorial, you will be able to understand quantum circuit execution, build a simple quantum circuit, choose the right backend simulator, execute the quantum circuit, and analyze the results. Before getting started to create a quantum circuit, you need to install the software development framework, which is Qiskit Air. This framework supports the QSM simulator as a backend simulator. So you need to install this using pip install Qiskit Air on your Jupyter Notebook or Google Colab. Then you can import some functions and classes from the Qiskit module, Air, Execute, and Quantum Circuit. And now we're going to create and execute simple quantum circuits. To do this, you can first create a simple quantum circuit using the quantum circuit class from Qiskit. And this quantum circuit function or class takes 2 parameters. integer parameters. Those are, for example, 2 by 2 bits. The first two represents the 2 qubits in the quantum circuit, and the second number 2 represents or specifies the 2 classical bits. Now we're going to use the Hadamard gate, and I can use I can rename this to quantum circuit, not quantum register. You can watch a previous tutorial about quantum register and classical register. I have demonstrated practically using Qiskit and Python. So now quantum computing had the first position, so-called Hadamard gate, or which is called H gate. And the second one is the CNOT, or controlled knots. Because I have a multi-qubit quantum circuit, and I can use a Hadamard gate and the controlled knot gate. So the first is the controlled qubit, and the second position qubit is the target qubit in this controlled knot gate. Okay, now I'm going to use the measure operation that measures the result of the quantum circuit. One, again, there is also one. And going to choose the air backing, which is the backing. So the simulator in this case I'm going to use is air dot get backing. This simulator is called KSM simulator, which is used as a backing. Now going to execute the circuit on the simulator. So that is called the jobs that going to execute the circuit on the simulator I have used as a backend and pass the simulator. And here going to use shorts, which the number of times that the simulator going to execute. And finally, get the result from this. So that could be done using Gates counts method. So I can pass QC there, and here is what. And finally, going to print out the result to analyze. Okay, let me explain this lines of code. The first, I have created a quantum circuit with 2 qubits by 2 classical bits, and also includes a Hadamard gate and a controlled NOT gate, and also a measurement operation, which is measure that measures the result of quantum circuits in the classical bits or qubits. I also choose the KSM simulator as the backend for simulating using air.get backend. I then execute the quantum circuits on the chosen simulator, and I use Qiskit method. And this Qiskit method, I also pass shortest as a parameter, which specifies the number of times that the circuit is executed to collect the statistics. So I just specified 1024. I then retrieved the count results or the result counters using get counters method and prints the result to analyze the quantum circuits. Now let me run this code and let's see the output of the circuit. This is the output of this circuit I have constructed or created. So this circuit, the result of this circuit has two qubits. So it is the keys 00 and keys 11. The keys 00 represented the possible measurement outcomes. And the quantum computing, this 00 can signify that both qubits were measured as the state 0. And 11 also represent that both qubits were measured as the state 1. So the values in the 00 indicate that the frequency or count of each measurement outcomes. Therefore, the 00 was observed 506 times and 11 was observed 518 times during the execution of the quantum circuit. So this is simple quantum circuit. You can create your own simple quantum circuit using Qiskit in Python program on Jupyter Notebook. By leveraging the capabilities of Qiskit, you can gain valuable insights into the principles of quantum computing through the execution of quantum circuits. This practical engagement serves as an essential starting point for comprehending the potential of quantum computing and its applications in various fields such as algorithm optimization, cryptography, machine learning, and artificial intelligence. So your feedback is invaluable. If you found this tutorial helpful, please like, share, and subscribe. Leave your comments or questions in the comments below. Stay tuned for more quantum computing and AI tutorials by subscribing to my YouTube channel. Thank you for watching. Hello everyone and welcome to this fundamentals of quantum computing tutorial with Qiskit. This tutorial provides a practical guide to implementing visualization of various quantum concepts using the Qiskit framework. The tutorial also covers the creation of quantum circuits, drawing a quantum circuit, and plotting historical data of quantum data. If you are interested in learning more about quantum computing programming, I encourage you to watch this tutorial. So let me show you how to construct visualization and drawing a quantum circuit. First of all, you need to install the framework which is called Qiskit Air, which supports the backend simulator. Then import the necessary classes from Qiskit modules such as quantum circuit visualizations from Qiskit.visualization module. Now create a quantum circuit using quantum circuit class. And pass two qubits and two qubits classical qubits. Then you can use the Hadamard gate in the first position of the bit or qubit, and also controlled NOT gate in the first and the second position of the qubit. Because this is a multi-qubit quantum circuit, and also measure the quantum circuit result using measure operation. Okay, now the next is drawing the circuit. I'm sorry, this is uh, passing the qubits in the first and second in both qubits, so that's why it generates an error. Now we have constructed our quantum circuit with two qubits by two classical bits. Now the next is drawing the quantum circuit. So to draw this, you can basically use print quantum circuit dot draw, or you can also use another method. So this is the way how you can draw a quantum circuit. So this is the circuit. You can use. You can also use a circuit visualization from visualization dot circuit draw, and you can pass the quantum circuit. This is what draw, okay, not draw. Yeah, it is the same, so you can use either the first method or the second method to draw the quantum circuit. So in this case, this code just demonstrates how to create and draw a simple quantum circuit using Qiskit. It also includes a Hadamard gate, H gate, and the controlled NOT gate, which is CX gate, on two qubits, so followed by measurement operations. So this, so you can understand all the symbols of this quantum circuit. So thus, for example, H line represents or indicates the sequence of operations performed in the quantum circuit. So H represents the Hadamard gate operation applied to the qubit related to Q0, and at Q1 is the controlled NOT gate or CXX gate, and this is the classical register in the which stores the measurement of the quantum circuit. So you can understand each symbols represented in this quantum circuit by looking at the internet. Okay, the next I will show you is plotting histograms of data. So you can plot the histograms of data. First of all, you can import uh, the air and execute functions or classes from Qiskit. Now let's I have already constructed the quantum circuit, and I'm going to plot the histogram data of the quantum circuit. So first of all, let's simulate the circuit. So I'm going to use the backend simulator in this case. So the backend simulator going to use is air simulator. Dot get backend, and here I just use the backend simulator, which is air simulator, and going to obtain the results by executing the simulator using execute method, and I pass the quantum circuit and the simulator. You can use shorts here, for example 1, 2, 4, and then you can obtain the result by calling result method at the end. No backend matches, okay. Yeah, here I just mistyped the backend simulator that is called. Okay, all right. Now going to plot the histogram. So to plot the histogram, I can import the Qiskit visualization and import the histogram from Qiskit visualization. Now let's get the counters, the number of counters that the circuit measured. Result dot get counts, and I can pass QC. Okay, now going to plot histo, and I pass counters to this, and you can see the data. Okay, yeah, all right, this is what the data, and this code is a quantum circuit simulator using the Qiskit Air simulator, and it's just extracts the measurement results and plots the histogram of the outcomes, showing the probability distribution of the measurements. So as you can see here, there is a 0 state and 1 state. So the both qubits can be executed 491 times in the 0 states and also 533 times in the 1 state. So the keys 00 and 11 represent the possible measurement outcomes in quantum computing. So 00 can signify that both qubits were measured as the state 0, and 11 can also represent that both qubits were measured as the state 1. So in this case, the values 491 is indicates the frequency or count of each measurement in the 0 states, and also 533 is also indicates the measurements outcomes of the state 1 which was observed during the execution of the quantum circuit. So as you can see this tutorial, so you can visualize the quantum circuit by drawing the quantum circuit and also plotting the histogram of data of the quantum circuit using Qiskit and Python. Thanks for watching. Hey everyone, welcome back to today's lesson. Today I will explore the fundamental concepts of quantum swarm optimization algorithm. So by the end of this tutorial, you'll be able to understand the algorithm and implement the algorithm using Python program. Please write comments in the comment section of this video tutorial. Also like, share, and subscribe. Let's go. The quantum-inspired optimization methods such as the quantum cut swarm optimization algorithm, which are designed to harness the principles of quantum mechanics to enhance classical optimization algorithm. So the quantum cut swarm optimization is a variation of the cut swarm optimization algorithm that incorporates quantum principles. So to create a basic version of quantum cut swarm optimization in Python, you can follow this algorithm steps. The first one is define the problem. So you have to define the problems. What is the objective function that you wanna minimize or maximize? What are the constraints on the variation or solution? And then initialize the cut swarm. This can be done randomly or by using a heuristic method. Each cut should be represented by a position in the search space. Then the third step is update the cut position. So the cut position can be done using quantum cut swarm optimization algorithm. So this algorithm combines the cut swarm optimization algorithm with quantum mechanics to improve the accuracy and avoid local optima. And the fourth step is evaluate the objective function for each cut we defined here or initialized here. So we're going to the fifth step. So the fifth step is update the global best solutions. This is the position of the cut with the best objective function value or so far. Then we're going to repeat the step three, update the cut position, evaluate the objective function for each cut, and update the global best position, and repeat until the uh, initialization or the termination or the terminate criterion is met. So this could be a maximum number of iterations, a certain accuracy threshold or a stagnation in the objective function value. Now we're going to implement the algorithms in Python. So to do this, first import NumPy and the function, define the function to optimize. So this you can replace your this function with your own objective function. So let me define a fitness objective function to optimize that. This function takes x parameter and is going to return the sum of I square for every I in the iteration or in the X. X is a list of iterations. It's list of positions. So it's going to iterate and finally just sum up together and return the sum of that result. Okay. Now I'm going to define parameters. The parameters are, for example, the number of iterations. Let me define, for example, 100. It is up to you. Number of cuts, how many number of cuts? Here, 5, for example, and dimensions. The number of dimension, for example, 2, h bar, which is the value of h bar is 1.05, which is actual initial value for 5718 e, which is the power of 10 raised to minus 34. Okay, so once you define these parameters, we're going to understand what are the uses of these parameters in our optimization algorithm. So I will explain the usages of this algorithm step by step. So the first one is number of iterations. This parameter represents the number of iterations or optimization steps that the algorithm will perform, how many number of iterations can be performed. And in each iteration, the algorithm updates the position of the cuts based on certain rules to improve the overall speed. Because based on the number of iterations, it's going to update the cut position, evaluate the objective function for each cut, update the global best position. So it's going to iterate from step 3 to step 5 until a termination criteria is met, which means until the number of iterations is greater than 100, okay? So the algorithm updates the position of the cuts based on certain rules to improve the overall fitness. We're going to apply the quantum the quantum principles rules. And the second parameter is the number of cuts. This parameter denotes the number of cuts or agents in the swarm optimization algorithm. So in the context of cut swarm optimization algorithm, the cuts represents the individual agents that are part of the optimization process. So each cat's position in the search space is updated iteratively to find the optimal solution. And the search parameter is number of dimensions. So here, this is S. So this signifies the number of dimensions in the search space. In the context of optimization, especially in multidimensional optimization problems, the search space can have multiple dimensions that define the possible solutions. Each dimension represents a variable or a parameter that can be handled to optimize the objective function. Okay, and the last parameter is h bar. Basically, this parameter pronounced as h bar. In the context of provided code here, it's used as a scaling factor or a quantum-inspired constant. It serves as a fundamental constant in a quantum mechanics. So this is a constant, like other constants, for example, pi. Pi is a constant. Like that, this is a quantum constant, the fundamental constant in quantum mechanics, which is relating to the quantization of physical properties and is used to introduce quantum-inspired behavior into the optimization process. So its value is 1.0545718 times 10 raised to minus 34 meter square kilogram per second. Okay, now I'm going to initialize the position of the position of the catches. So catches here np dot random we just pass the number of cats and the number of dimensions. So here we just initialize the position of the cats, and we also initialize the base noun positions and fitness values. So the base positions is cat's dot copy. We copy the cat's position initially defined here, and that is the best positions in the fitness. And we also find the best fitness. So np dot array, we can fitness function. We call the fitness function we defined here that's going to return the sum of the fitness. Okay. Here we just pass C for every cut, which means in the cuts. Okay. So that would be iteratively select the best fitness. Okay, that's the function optimization. Okay, now so far so good, and now we are going to define the main optimization algorithm or loop, and for every in the range of, this is elimination mechanism. We just don't need to use any value in this iteration. So I just ignore, but I used to iterate the optimization algorithm. So I'm going to implement optimization algorithm in the each iterations we defined here. 100 times of iteration can be performed in this algorithm. Iterations for every I in the range of the number of cuts. In this number of iterations, I also iterate over each cut I have defined in the swarm. And now the next is quantum or quantum inspired update rule. So that is the base thing here in the iteration. We are going to update the quantum inspired update rule. So here, the position of the cat at the position of I is going to update that, and we use the sign function here. So I use h bar, which is a constant in the quantum mechanics, and multiplied by the cuts at position I. Okay, at position I. So it's going to update the cuts here, update the cuts position, and evaluate the objective of the function for each cut, and update the global based position here. And so now update the position. If the fitness improves, so the current fitness in this case is fitness function. I call that fitness function, and I pass cuts at position I, and if the current fitness, which is less than to the base fitness, at position I, then the base position can be updated here. Base position is I, position I could be the cuts position I. So I am updating the base position, and the base fitness can be here based on that base position is here. So which means updating the global base position. Okay. And now the base fitness at position I could be the current fitness, okay, in the iteration. So this iteration, these steps can be performed until the termination criteria is met. So it's going to iterate 100 times based on the number of iteration, and it's going to update the cuts position, that is here, the cuts position, and update the base position and base fitness position as well. Okay. So now we have finished implementing the algorithm. We are going to print the values. So this could be outside of the loop. For every, can we print the base positions and fitness values for every I in the range, in the range of the number of cuts. We can print cut at position I, position, the best position. We call the best positions at index I, and the fitness. So the best fitness at position I. Okay, now going to run this algorithm and see the output, the values of the best positions and fitness values together. Okay. Okay, here there is error. Sorry, this is what in the bracket, so I forget putting the brackets. That's why there is an error. And here there's also that is the type error. Best position is not defined here. Positions. I just put I here. That's why this is typo. So don't worry. Yeah, the cat at position zero is the value, this one, the position, the best position is this one, the fitness 0, 0, positional, and so on. So this is what the algorithm of this, the quantum cat swarm optimization. So this algorithm basically demonstrates the quantum path optimization algorithm. So you can replace this function with your own function, and you can learn how to implement this algorithm classically. So this example basically integrated a basic quantum inspired updates rule using the sign function, using this uh, sign function applied to the position of the cards here, the position of the cards. However, it is important to note that this example is a simplified version and doesn't fully capture the intricacies of true quantum cat swarm optimization. So more advanced version of this would require a deeper understanding of both quantum computing principles and the CAT swarm optimization algorithms. I strongly recommend that for a more complex implementation of quantum CAT swarm optimization algorithm, you might need to refer to the recent research papers. Okay, because there is no framework that already implemented this algorithm. So this is what a classical example of quantum cat swarm optimization algorithm in Python program. So I hope this video was helpful. Don't forget to like, share, and subscribe, and also write your comments or thoughts in the comment section of this video tutorial. Thanks for watching today.